when Q is 0 means your acceleration of process noise which is uncertain is 0, and when this Q is multiplied with the covariant matrix, this is covariance matrix, okay, 4 by 4 matrix, then also 0 means your Q is 0. So if your covariance matrix is 0, then the filter believes that it has accurately give you the ideal response, and it will accurately give you the perfect response. But this is undesired feature. Undesired feature. So we do not want, and in this case, your filter gain also converges to 0. Filter gain also converges to 0. The state exclusion covariance converges to 0. Okay, because your covariance, your initial covariance is 0. So when you apply the filter, then the filter output the state covariance matrix. The state covariance estimation covariance matrix means this matrix estimated. This is output of the Kalman filter will becomes also 0. It converges to 0. So the reason is simple, is hangs on the assumed perfect noiseless constant velocity motion. So, and in practice such as assumption usually does not hold except for a short period of time. Like this, will show you the ideal response at Q is equal to 0, and at Q equal to 0, your position and velocity is converges to 0. The predicted, this is dotted line predicted, and updated means predicted means x bar, and updated means the output of the Kalman filter. Updated line, the output of the Kalman filter, and similarly the velocity and position converges to 0, and also the filter gain for position and velocity converges to 0. So in the ideal response or undesirable feature, when covariance is 0, your filter will convert the value of the position and velocity to 0. For non-zero values of Q, the filter is seen from figure 2 and 3 to reach steady state quite rapidly in few time space. For example, figure number 2, which shows the result in a motion, results on a motion with Q equals to 1. The steady state filter gain is this one. This is acceptable. This is acceptable. And figure number 3, which corresponds to a strong process 9 Q equals to 9. If we make it higher, then again this is undesirable, because that will model a high unpredictable motion. And the steady gain is higher. So in this case, when you see the figure, you can see the higher gain due to the higher process noise. Q equals 9, higher gain leads to a larger state variance. Means Q will become larger, and which result in less accurate state estimate. This will become, when you increase the Q up to 9, then 9 multiplied by Q matrix, then this will be larger, and this result in less accurate state estimate, output of the Kalman filter. So, this is the case when Q equals 1. So as you can see, this is not ideal. This is some like this one. Okay. So again the Kalman filter shows the very good result estimated the dotted line and the two lines of bold line, and this is the error. Okay. So previously the error is a straight line ideal. Okay. Now the error, as we can see, that is correspond to this trajectory, and this is predicted state estimate position and updated state estimate position, and this correspond velocity variance, and this is your filter gain for position and velocity. Okay, and this is the case when Q is 9. Okay, then this is a very unpredictable motion. Unpredictable motion means we cannot predict the motion. It goes from this start from here, this from 0 and goes like in the minus sign, very unpredictable motion because of higher covariance. Okay, and as you can see in all these figures, the true trajectory is different. Although model same model, true trajectory is different. Why? Because the trajectory is generated by this equation. F of k okay, and with the trajectory is generated with this equation, having the covariance q. Okay, having the known covariance q, vk is normalized by 0 mean and covariance q. So here, if you change the q and generate the trajectory, suppose if you let the q is a 9, then according to this, when you input this q covariance in this, then it will generate unpredictable motion like this. Again, if you use this equation and estimation algorithm, if you follow this trajectory to estimate the state of the this trajectory. Okay, so the trajectory of the first position is generated with this equation. Now the whole trajectory will input to the estimation algorithm. When estimation algorithm is applied, when the trajectory is applied to the estimation algorithm, it will give you the results according to the trajectory. Okay, so here when q is equal to 9, your the true trajectory change, because of we have generated the trajectory with this formula, and similarly in all three figures, the trajectory is generated by this formula. Okay, and at the high value, your filter gain is very high due to high covariances. Okay, so very unpredictable motion of the object, and this is a very this is according error. This is corresponding error. So corresponding error is also at the minus sign. So and this is similarly this is very high gain like 0.9, 0.94, but high gain we don't want the high gain. We want that covariance should be low, so that we can get accurate statistic met. And this is the predicted position and updated position, and similarly this updated and predicted velocity. Okay, so you can see the effect of the covariance on the filter. So the covariance filter, covariance of the Q is based on the process noise acceleration. If you increase the acceleration, the filter gain will become high. Why high? It will become high because the covariance, initial covariance is high, the trajectory covariance is high. Then when it's applied to the estimation algorithm, your filter covariance will become high. Your filter coverage will become high, then filter gain high. But it will reflect the state estimation to less accurate. Okay, and then there are other two important things. Okay, it is clear. Although you choose the Q equals to 1 and you maintain the covariance to low, okay, and your trajectory output came out, okay, but you have to verify the consistency of the filter, whether your filter give you accurate information or not. Means in this case, even in this case you have to verify the consistency of the filter, that the filter gives you the accurate information or not. Okay, so what is consistency of the filter? Consistency of the filter in the problem of estimating of parameter, that is constant. Consistency of the filter, that is static filter, was defined as the convergence of the estimate to the true value. Means if filter estimate converges to true value, then it is consistent. And in case of dynamic system, no convergence of its estimation occurs. Okay. In case of dynamic system, we can define the estimation. We can define the consistency with the help of associated covariance matrix. In case of dynamic system, we have to define the consistency of the filter with the help of covariance matrix, because your filter gain, which is multiplied with the Kalman filter, is totally dependent on the covariance. As you have already seen in the calculation that your filter gain is calculated by the covariances. All parameters of covariance that are calculated with the filter gain. So your in case of dynamic system, we cannot define that if the estimate converges to true value, then filter is consistent. No, in this case there is no convergence of its estimation occurs. So we have to define the with the help of covariance matrix. We have to define the covariance matrix satisfy the two property of controllability and observability, and we have to satisfy some test of consistency. Okay, suppose state estimator is called consistent if its estimation error satisfied. So consistency of the filter satisfied that your error has a zero mean. Your error the expected value of error has a zero mean and covariance, and the magnitude of this error is defined by the covariance. Okay, your error has a zero mean. Okay, uh, zero mean and covariance. This covariance is a filter covariance, means the estimated covariance. This covariance is associated to this covariance, means this is output of the filter. If you remember from the previous lecture, this is calculated by the filter, the updated state, the final step of the equation, Kalman filter update equation, and this is a corresponding updated covariance matrix of this state estimate. So it should have a zero mean and covariance matrix. So this is two conditions: have a zero mean, the estimate are unbiased, and have covariance matrix is as calculated by the filter. So practically you can define consistency that your error okay. So this is your error, that is the true value. This is the trajectory value, the dynamic equation, the dynamic equation number 1 minus the estimated the filter output state estimate. Okay, this is the error. This is initial covariance. Initial covariance. Okay, that is also from the trajectory dynamic equation, where V of k okay, because at the start, at the first two scan, you have to start with this one. You have to start with this one. But initially you do not have a state estimate. You just have the dynamic equation. You just have at this time you just have this equation, this value. So you have to obtain this value so that you can apply the Kalman filter. Okay. So this is applied. This can be obtained by the two-kind initialization. At the same time, this you have to require this one. Okay. So this is the same. This initialized. This is, as we can say, this is initialized covariance. This same used in this here, initial covariance. That initially you have initial covariance that you have applied for the correct initialization. Okay. This is obtained by two-kind differencing. Okay, and this is the chi square distributed probability of false alarm. So due to other false alarm, maybe their two trajectory the filter is confusing with the true trajectory because of many false alarms. So we have to check with the probability of the chi-square probability. If this satisfies with some threshold like 10, if this is less than, again this is depend. This value depend on the surveillance area. If you are working on this, just in this room, this is a small room, then you can set with this small area. Okay, for example, in my case, I work over 1000 meter, 1 kilometer to 1 kilometer, then I set 20. If this equation is less than or equal to 20, then this is a true, the filter is consistent. The filter is consistent. Okay. So we have to check the filter consistency with this formula to check the covariance, of the filter. So this is filter covariance, filter output. We have to check the filter output covariances. If this is satisfied, this equation, this is a chi-square distributed probability of false alarm. Okay, scalar quantity. So as you know, the PDF of this state estimate have this state estimate and this updated covariance. Then the consistency will be based on the fact that under LG assumption, the linear Gaussian assumption, it should satisfy this equation. Okay, so that is average squared norm of estimation error indicated above has to be satisfied chi-square distributed probability of false alarm, and this is most important and can be tested only in simulation. So at last, since the filter case is based on the filter calculated error covariances, it follows that consistency is necessary for filter optimality. Wrong covariances yield wrong gain. So we have to check the covariance with this equation. What is this?
Oh. It's a book.
So again, another important thing, to find initialization. Okay, as we have discussed, like this one, Z1 and 2, Z1, Z2, Z3. 1, 2, 3 is a K scale. This is K. K equals to 1, K equals to 2. Your filter update start from K equals to 3. Here is a no estimation for the trajectory because your estimation algorithm will use the measurement information of 2 scan to initialize the track. Here. Okay. Then this will input to the Kalman filter to get the prediction of for the next scan and likewise. Okay. So as we have discussed that we have to compare like this one line. This will give you velocity, and this should be less than or equals to maximum velocity. So those measurement will satisfy this equation will initializes or track. Okay. So in that track, suppose track 1. In that track, what is value of what is value of x of k, okay, and what is value of p of k, okay. What is value of this one, this one? This is the same z2 and z2 minus z1 over t. This is z2 and z2 minus z1 over t velocity. Again, this is two-dimensional position, and this will be also two-dimensional velocity. And this is the r over t, and r over t 2r t square, 2r t square. So initially you have to initialize the track with this covariance. Okay. So usually when you open some papers, when they discuss about two-point initialization, they denote this thing with the x of 0 and 0, because initially it start from this one, so they assume that they are this thing 0 0. Means the updated information is start from 0 and up to end. So although it uses the scale number 1 and 2 to get this information, and also in those papers they use this value here to satisfy the equation, this one. Okay, but you can use this information as well to identify, to verify that filter covariance is consistent, and this filter this covariance consistent is enough for verifying the state estimate, that our state estimation or our calculation is accurate. Okay. And any question? Even when I program, I use this value. But if I choose this value, this sometimes get not enough information for me, because sometimes this covariance becomes higher. Sometimes this covariance becomes higher than this one, than this thing. This is fixed. This is fixed. Okay, this is fixed value. But sometimes this will become higher because it is calculated by the filter. Calculated by the filter covariance in each scan. In each scan filter calculation. So sometimes it will become higher due to calculation and other noise and state estimation, because motion is unpredictable. Okay, so motion is unpredictable, especially when the motion is not a constant velocity motion. When the motion of target is maneuvering like this one or and like this one, then in this case the filter motion is very unpredictable. So if we choose this fixed covariance, okay, then the selection of the accurate estimation will satisfy this equation and will hold consistency as well. Why? Because this covariance is used to initialize track. It means the track path use this covariance to initialize the track means it can be used as a consistency for the filter. Okay, it can be used consistency for the filter. This covariance matrix. Okay, clear? Now your first mid assignment, 10 marks. Okay, so 5 marks is for simulation, 5 marks is for report and presentation. Okay, so consider two-dimensional position and two-dimensional velocity. Okay, trajectory of the object defined by you have to select any point. So every guys have to choose different point. Okay. For example, in our example, we have choose 0 and 10. In the previous example, for one point, we have choose 0 and 1. So suppose this guy have choose the initial point like 200, 200, and velocity 10, 0. Suppose he choose this vector that your target is start from x position 200, y position 200, and moving in the constant motion with velocity of 10. Then other guy should choose different position like 300 and 50 with different velocity like 50 or 0, not necessarily the x velocity, it can be the y velocity, or it can be both velocity 5, 10. So every guy should select different trajectory. Just the first point, you have to choose first point. Okay, and measurement equation x wk. Okay, this is a problem statement. Your problem statement is defined by this dynamic equation, measurement equation having both things are corrupted with a noise, this one and this one. Okay, so you have to, first step is to generate the function for parameter. First step, write a program for function parameter. Okay, and here you have to assume like scan, suppose 50 scans. 50 scan means the case start from 1 and end to 50. Okay, and suppose the sampling time is 1 second, and suppose q is equal to 0.75. Okay, if you make it higher, then the trajectory will become unpredictable. So make it 0.75, okay, or 1, and your r equals to 25 and 25 0 25 no 0 0 25. Okay, this is the measurement noise covariance R. This is the measurement noise covariance R. Okay, if you make higher, your noise is higher. If you make it lower, your noise will become lower. Okay, so you can make this thing as according to the area of the region. You can change it. Okay, if your area is larger, then you can make it to 25. If your area is small area, suppose 5 meter, then 5 meter, and still in this region area of surveillance area, if you make this, then very difficult because noise is very high, and in small area noise is very high, then your estimation result will become effective. So you can choose different value. Okay, this thing and this thing is very important. This depends on your area. Your area, if your area is smaller, then you make it smaller. Okay, because this is a noise covariance, and Q equals to again Q is the fixed value. I forgot the matrix. It is again given in the book, and this Q is multiplied with this one. Like here, multiply Q is I think 153 154 no 153 154 and 1, and this is t, by t, divided by t, by t, cube, square. Okay, so here I is identity matrix, identity matrix. Okay, and T is a sampling time. Okay, because sampling time is not necessarily the one. It can be quite 5, and it is depend on your problem. You can set any value time. So again, you have to take this matrix from the book. This can be, you can see in chapter number 9. Chapter 9, fundamental of object tracking. Okay, and also estimation with application to tracking and navigation. In this book also you can find this value. And in this chapter number 9, you can find the two-point initialization. Okay. First thing you have to decide this thing, and the simulation runs. Suppose n equals simulation runs. N equals to 100. Okay. You all have to run this program for 100 times. Okay. And second function is for the trajectory generation. Here first function and second function trajectory generation. Suppose you choose this one 355 and 10. Then you have to apply this thing for I scan 1 to n scan. Use this formula x a k plus 1 f x of k and okay. So remember, first for trajectory generation you do not have to add the noise. You do not have to add noise, because if trajectory, if you use this one, the trajectory will be have a smooth platform. You have to add the noise in the estimation algorithm. Okay, and that is not here. You have to use this thing, and you have to add the noise in the measurement, not here. Okay, for I scan 1 to n scan zk plus 1 equals to h x of k w x square and okay. So this function will give you the data for trajectory up to 50 scan and for measurement data up to 50 scan. So here you consider the noise over here, and then you apply the estimation algorithm. But before, another function for initialization. So here parameters are z2, z1, okay, r, t, okay, and other f, q, this thing. And here you generate suppose first you have to calculate the length of z2, okay, then length of z1. Suppose this is 1, this is 2, okay. Then for length of I equals to 1 to measure 1, okay, you have to select, because in this length there are maybe 5 measurements, 6 measurements, I don't know, and there are some maybe 2 measurements or 7 measurements, we don't know, because number of measurements in each scan are uncertain, okay, maybe 5 to, okay, it depends on the sensor. Then select first measurement, I measurement, okay, and then again another loop for j equals to 1 to 1 to measurement 2. Then again here you use the formula for z2, like this one, I minus z j, okay, and here you check the velocity, okay. In parameter you have to mention the v maximum, suppose 10, again depend on the velocity. In this case you can set it 20 meter per second, and then okay, and then when you obtain here the x, because if this is selected, then this is your x, okay, and covariance like this one, r over t, 2rt and r. So this will input to the Kalman filter, okay, this will enter to the, this will, you have to input to Kalman filter prediction, x of 0, p of 0, and the parameter f and q, f and q, okay. Then this will give you k plus 1, okay. After this verification, those measurements which satisfy this equation will be selected for x naught, and that will be input to the Kalman filter, and this Kalman filter will calculate the prediction. Okay, prediction for the next scan. And again, you maybe remember the other step. You have to calculate the measurement prediction. Okay, and then covariances, innovations, and other formulas we have already studied in the last lecture that I have written in the board. And then the measurement prediction, measurement covariance, then residual, then calculation of filter gain, filter covariances, then apply the Kalman filter update, and finally the Kalman filter update equation. This will input here x of and here other parameters are the W filter gain and S covariance and also the residue. The residue is the difference between the sensor measurement and the mean of the measurement. Okay, this is sensor measurement and minus this is the residue. Okay, in this is called the innovation. Okay, you have to check the difference. What is difference between this one, the predicted measurement? You have to check the predicted measurement difference to the current scale measurement. This is sensor measurement. This is sensor input. Observation. This is observation, and this is you have calculated from the measurement prediction. This is you have calculated the measurement prediction, and this is the sensor measurement. This is measurement prediction. So this is inputted to here to get the output x of so for your guide you go through this chapter, fundamental of object tracking, and you can see how you have to initialize, because this is easy. You know all these parameters are used in this algorithm, so you can see how to initialize this thing, and what is this, how to calculate this thing, all mentioned in this chapter. Chapter number 9 is practical implementation. Okay, and then another guidebook is estimation with the application to tracking and navigation chapter, and the chapter number 5, application to what's the name? Application to estimation. Application to this one. Okay. So every guy should decide the vector, initial vector, and apply the formula and run it in MATLAB, or you can use any other language like C. Okay, and run the simulation for 100 times and obtain the result, and you have to make the report, the assignment report, like you have to write the some introduction for the estimation, why it is used, and where we can apply, and what is the benefits for the application. Okay, and then problem statement. And in problem statement you can write this equation, and then method. Your method is just first initialization, then prediction, then measurement prediction, then residue, then filter calculations, and then Kalman filter equation, and finally the results, and then conclusion. Okay, and then you have to prepare the presentation, and you have to here after mid-exam you have to present this here. Okay.
Due date. Due date.
Due date
No, after mid-exam.
after meeting.
화요일이냐 목요일이냐 그것이 문제보다.
When what day?
화요일 영어로 뭔지 까먹었어.
Tuesday.
Your exam will end up to 30 April. Okay? The 30 April. And then your first class of the mid-exam is 4th
Please.
May.
Hmm?
So 4th
4th May?
4 May is okay?
Ah yes.
May 4.
Happy to be.
Okay?
May 4 is presentation day.
Presentation and submission of the report. Okay?
Happy. Happy.
I have a question about problem. The dimension and simulation runs is fixed, and other parameters is we can choose.
Yeah. Other parameter like this and this thing you have to choose, and this thing you have to choose.
T is time is fixed.
Time is fixed, okay, time is fixed, and also area. Also area. Your and y minimum, y maximum, x minimum, y x maximum. You have to choose the area, and all guys should choose different area. So depending on the area, you can choose this one. So actually, this is identity matrix where you have to multiply R. So R is your measurement noise, like this one. So R you can choose to 5 up to 25, depend on your area. And F is also fixed. F is also fixed. It is also 4x4 matrix, and this is I, IT, I and 0. But I'm not sure. You have to check this matrix in this chapter or in this chapter. You can use this printed. Both are same in this and this chapter, because this is fixed. Every Scientists use this value fixed. So again, this is identity matrix, and this is time. So if you are two-dimensional, 2 by 2 dimensional state vector, then it's 4 by 4. If this is a 3 by 3 dimensional vector, 3 by 1 dimensional vector, then it will be 9 by 9 matrix, and it's also 9 by 9 matrix. Okay. But at this stage, you should work for the 2-dimensional. Okay, I'm here. Before going to this equation, you have to add noise. Not here, because this is true value, and when you check for estimation error, you have to when you check for the mean square error, like this one, expected value of the mean value, x of k minus x of. So this is this true value. For the calculation of the estimation error, the x of k is a true value without noise, and this statement is with noise. So when you generate the measurement set, okay, then here you have to add the noise of v here. Again, in this book, you can find the how can you add the noise. So this noise and this noise is a Gaussian noise. Okay. So you can add like MATLAB command, this thing, and 2 row, and scan. You can use this thing. And for adding a noise in this thing here, and you can add this thing, but here for adding up this noise, you can have to see in this chapter. Okay, because again this depend on the surveillance region. This again depend on the surveillance region. What is the total area? Because in that area, how much amount of the noise entering to the surveillance region? Because this sensor, it's a sensor in the sensor environment, outside environment, what are other noises? As you can see here camera, but there are many people, and other than people there are many objects. So a camera can observe this furniture, and also tube lights, light, everything, window, curtains, everything. So here the addition of light is not this one. You can add this to this equation, but not here, because here there are many other observations. So it depends on the surface area. So you have to check this, and also you have to check some paper. So this is very widely used, and you can easily find it from paper and from book. Okay, and after doing this, you will able to apply this kind of estimation algorithm to any other application in your field. Okay, so very important. If you have any problem, you can come into my office and I will explain to you. Okay. Okay, and anything else?
No.
No.
So 5 marks is for simulation and 5 marks is for report and your presentation. Okay? Thank you.
Thank you.
I don't have yours.